In this video, I will show you how to use the probabilistic features available in ZSoil to analyze an example tunnel construction in an urban environment. Here you see a longitudinal section through the tunnel, where you can see that it will be constructed underneath existing buildings. And this is a cross-section. For the sake of this example, I will keep things simple and work with a 2D plane strain model. This can be a valid assumption for certain project stages and desired outputs, and keeps the time for the model creation and the subsequent computation small. Of course, we have to take care of certain things in our model to reasonably approximate some important 3D effects. For example, we need to somehow reproduce the staged construction of the unsupported excavation and the installation of the steel profiles and the lining, etc. I will approximate this in the following way. The excavation in the 2D cut will be introduced gradually, using an existence function on the elements to be excavated in combination with an unloading function. This is a useful feature in ZSoil, which deactivates the elements according to their existence function, and at the same time introduces equivalent forces along the boundaries of the area of removed elements. These equivalent forces are then gradually reduced to zero according to the defined unloading function. In this way, it is possible for us to decide at which point in time during the excavation what part of the lining will be introduced into the model. In a simplified way, this reproduces the temporarily unsupported phase during construction in 3D. So in specific terms, I will introduce the lining, represented by beam elements in ZSoil, at 60% unloading. By doing that, I'll have the first 60% of the excavation unsupported and the remaining 40% with the lining installed. So now, let me quickly show you the finite element model in ZSoil. I will not guide you through the creation of the model, as the focus of this video lies on the probabilistic capabilities of ZSoil. Let us start with the material definitions. Material number 1 is for the soil, and therefore has the hardening soil with small strain stiffness material formulation, or HSS in short. It represents a very good soil, namely the molasse in Switzerland, which is actually some kind of rock. The secant stiffness at 50% failure load, called E50, is 100 megapascals. The internal friction angle is 30 degrees and the cohesion is 75 kilopascals. Furthermore, in this constitutive model, we also define the odometric modulus, the elastic unloading-reloading modulus, as well as the elastic modulus for small strains. Material number 2 corresponds to the steel for the beams. The profile cross-section is that of a HEA 200, and they are placed in a distance of 1.5 meters from each other. Here, the Young's modulus of the steel is defined. Finally, material number 3 is for the contact elements between the lining and the adjacent soil. Then let me next show you the defined existence functions. The excavation starts at time 1. So the first existence function controls the disappearance of the elements to be excavated. Existence function number 2 controls the appearance of the steel profiles. And, as you can see, they are installed at time 1.6. And as the unloading function for the excavation is defined to linearly drop from 1 to 0 between times 1 and 2. This means that the first 60% of the excavation will take place without the lining, and the last 40% will be taken by the steel profile. So up until now, the finite element model was built up just like any other deterministic model, and I will just run the normal deterministic calculation now. And then, by going to the post processor, I can do a quick check if everything was implemented as planned. Here are the calculated time steps. You see that at time 1, corresponding to the start of the excavation, all elements are still present. At time 1.6, the excavation is taking place, but the steel lining does not yet exist and is only just about to appear. And then at time 2, the steel lining is present. Maps allow you to display quantities like stresses or displacements on the whole model domain. I can also inspect the bending moments in the steel lining. There exists a hinge at this location, which is in accordance with the displayed bending moments. Now let me continue to carry out a probabilistic analysis. I start off by defining my random variables. These can be any material property, load function scale factor, existence function time, and more. Anything that is supposed to be probabilistic and not deterministic in the model. For material 1, from group nonlinear, I choose secant reference E modulus at 50% of QF. This is E50. Then I'd like to redefine the very long label and just call it E. Then I add another random variable from material 1 from group nonlinear, namely the friction angle. And finally, from the same group, the cohesion. And then, apart from material parameters, I would like to put some uncertainty on the time at which the steel profiles are installed. For that, I can also create a random variable based on an existence function, namely existence function number 2. Leave period as initial material. And I would like to choose the starting time of this existence function as our random variable. So I've now defined the installation time of the steel profiles as a probabilistic random variable with a mean value of 1.6. I've renamed the last 3 random variables to phi, c, and lambda for better readability. Next, I will choose the distribution types of the defined random variables. The available possibilities are uniform, Gaussian, log-normal, and Gumbel. The log-normal distribution often makes sense for random variables that can physically not become negative, as it ensures exactly that. So I will choose log-normal for the first 3 random variables E50, phi, and c. For full definition of the distributions, I also need to define the standard deviations. I like to think of them in terms of the coefficient of variation. It is defined as the standard deviation divided by the mean value. And for E50, I choose 20%. So for a mean of 100,000 kilopascals, this gives 20,000 for the standard deviation. Once the distribution of a random variable is fully defined, it appears visually in the diagram on the right. And it can be seen that the log-normal distribution only takes positive values for the random variable. So then I continue with a log-normal distribution for phi and choose a coefficient of variation of 10%, giving a standard deviation of 3 degrees. Analogously for c, with a coefficient of variation of 20%, giving a standard deviation of 15 kilopascals. Finally, for the construction time of the lining, I decide to choose the uniform distribution type and a standard deviation of 0.03. So now the definition of the 4 random variables is complete. But, as you know, the hardening soil small strain stiffness material model has more parameters than E50, phi, and c. For example, the odometric tangent modulus, the Young's modulus in unloading and reloading, the initial Young's modulus at small strains, or the earth pressure coefficient at rest, K0. Each of these could be defined as their own random variable. But oftentimes, instead of treating the choice of their value independently, approximate relations to other material model parameters are used for them. So instead of defining individual random variables, we can make them dependent variables to one of our defined random variables. Let me explain this in detail on specific examples. I have predefined such dependencies in the general settings, as I want to use the same ones in most probabilistic calculations that I run. They can be fetched with this button here. Add dependent variables for predefined relations in general settings. But let me show you how to predefine them as well. So I exit the random variable definition and go to the general settings. And as I've said, I have 5 dependencies defined here. Let me explain each one quickly. The first one defines a dependency of the odometric tangent modulus to E50, our random variable number 1, with a multiplier of 1. So the 2 variables will always be identical. Then, the unloading-reloading Young's modulus is set equal to 4 times E50, and the initial Young's modulus E0 is set to 10 times E50. Of course, these linear relations are just approximations and assumptions. They, however, ensure a certain degree of physical compatibility of our abstract material properties. The 3 defined dependencies of the stiffness properties ensure that all stiffness variables together are either high or low in relation to their mean values, and none of them is low while the others are high. The chosen values of the multipliers themselves are just examples here, and they depend on the type of soil. Some suggestions are given in the ZSoil report on the hardening soil model. Then, moving on, there's also a dependency of the earth pressure coefficient at rest on phi, according to Yaki's formula. K naught is equal to 1 minus sine phi. This is a very common assumption to make, and imposing this dependency here ensures that the formula is taken into account for all realizations of the random variable phi. Let me then just delete and redefine all of them for you to follow. Now I return to the random variables definition and can fetch the dependencies. They then appear in this list. That's it for the definition of our random variables, and I exit by pressing OK. In this example, I will add no further correlations between random variables. This would be another way to define a certain connection, termed correlation, between, for example, 2 material properties. Both properties would remain their own random variable and not be directly connected via a specific multiplier. Nevertheless, a certain statistical correlation would be enforced. One example of this could be to correlate phi and c. So then the next step is to generate a number of samples of realizations of our set of random variables. Each sample serves as input parameters for one calculation of our finite element model. The different samples are generated to well cover the probabilistic domain of our problem and will later allow the generation of an accurate meta-model. I choose to generate 100 samples. Once they have been generated, I can close this window. Then I need to compute each of the 100 samples with ZSoil by pressing Run FE Analyses. The progress of this is displayed in the progress bars of this little window. After a while, depending on the specs of your machine, the 100 samples have been calculated and I can close the window. Now it is time to define the quantity of interest of our probabilistic calculation. I want to take a look at the serviceability limit state in terms of the maximum settlement below the existing building. So let me go back to main, which will allow me to find out the node number of the node where I expect to find the maximum settlement underneath the building. This is the top node at the symmetry axis here. By going to Info, Node Info, I can pick the desired node, and its information is then displayed. It is node number 348. And additionally, we can see that the settlement in our deterministic calculation containing our mean values for the material properties is around 11 millimeters. Then I go back to probabilistic analyses and quantities of interest, where I want to add one of type nodal result. I choose displacement component y and specify node number 348. Confirm with set and exit with close. The defaults for the rest of the setting is correct, so I confirm with OK. Then, under Results Review, I can have a look at all the samples and their result for the quantity of interest that I have just defined. Values marked in green represent maxima of all occurrences and values in red minima. Note that our quantity of interest displacement y of node 348 is defined positive for heave and negative for settlement. So our minimum settlement of all samples is 8 millimeters and the maximum 24 millimeters. The definition of our quantity of interest lets me now generate a corresponding metamodel. For the method of metamodel creation, I leave polynomial chaos expansions, in short, PCE. There are also other methods available. If you'd like to learn more about this, I encourage you to consult the ZSoil manual. The generated metamodel relates our random variables E50, phi, c, and lambda to our quantity of interest, using the 100 computed samples. Once the metamodel has been generated, a new window informs us about the quality of the metamodel in terms of the leave one out error. In short, LOO. If you are happy with the resulting value of the leave one out error, you can accept and continue with the rest of the analysis. If it is, on the other hand, not small enough for you, you have the possibility of calculating a larger number of samples, which should bring down the leave one out error. Let's assume that I accept the generated metamodel. So I press OK and then close. Using the metamodel, I can, for example, perform a sensitivity analysis of our quantity of interest on our random variables. There are again different methods available to choose from. I choose the ZSoil method, as we have no correlated random variables. Otherwise, one could choose the SRC method. Again, please inform yourselves about these methods in the ZSoil manual. Run the analysis. Once it's done, you can close the window. Then, in the toolbar on the left side under Sensitivity Results, we can display the results in a chart. In this case, we can see that the stiffness parameter E50, and therefore also the other dependent stiffness moduli of the hardening soil model, have the largest influence on the settlement of the existing building. The strength parameters phi and c, as well as the time of installation of the lining, have just a minor influence. Next, I would like to perform a reliability analysis. For the quantity of interest, I choose the y displacement. Let's assume that the structural engineer has given us a serviceability limit of 2 centimeters. So I would like to know the probability that the settlement is smaller than minus 0.02 meters. I run the analysis with execute. Once it's done, confirm with OK. Again, in the left sidebar, under Reliability Results, you can, for example, look at the response histogram. And you see that the probability of exceeding 2 centimeters of settlement results in about 7%. The accepted probability of exceeding the serviceability limit state should be defined by the client together with the designer and the contractor. This is because the consequence of exceeding serviceability limit states is typically the cost of repair and not the total failure of the building with possible loss of life, like in ultimate limit states. Typical probabilities for SLS are maybe in the range of 1 to 5%. So our result is not far from that. Accepted probabilities of failure of ULS, on the other hand, are much lower, maybe something in the range of 10 to the -4 or 5. Okay, now let us look at another quantity of interest. For example, I'm interested in the probability that the bending moment in the steel profiles will exceed their moment of resistance. So for this, I go back to main. I display the results in beams. And here we see the resulting bending moments in the tunnel lining from the initial finite element analysis with mean values for material properties. Then I select all the steel beam elements like this. Under Lists, Elements, I can copy the list of selected elements. Then I go back to Probabilistic Analyses and Quantities of Interest, and maybe delete our previous quantity of interest if it is not needed anymore. Then I create a new one by adding element results. I choose Beam Moments MZ and paste the list of beam elements copied before. I press Set and then Close. I would like to include all time steps and choose the maximum of the absolute values of the bending moments, as both negative and positive bending moments are equally important. I confirm with OK, and the following message pops up. Quantities of Interest list has been changed. The meta-model, the performed sensitivity and reliability analyses results will be deleted. I'm fine with that and continue with Yes. I can go back to Results Review and you see that the input values here are still the same. But we have a new quantity of interest, which ranges between 26 and 47 kilonewton meter. Then I want to generate a new meta-model because the quantity of interest has changed. It would have been possible to define our two quantities of interest at the same time, but in this introductory example, I wanted to do it separately. In case of simultaneous definition, it would have generated two different meta-models, one for the settlement and one for the bending moment. Okay, I have a small leave one out error, which is good. Then I go back to sensitivity analysis, still using the ZSoil method. Once it's done, let's take a look at the results. You see that it looks quite different to the last sensitivity analysis. The influence of our four random variables on the maximum absolute value of the bending moment in the steel profiles is a bit more evenly distributed, with phi and E50 being the most influential. Then, again moving on to the reliability analysis, I choose as the quantity of interest the bending moments in the steel profiles. And I'm interested in the probability that they exceed their moment of resistance, let's say 60 kilonewton meters. I run the analysis with Execute. Once it's done, confirm with OK and close. I'll again show you the response histogram. And you see that the probability of exceeding the moment of resistance in the steel beams, or the probability of failure, is 2 times 10 to the -5, which could be acceptable for an ultimate limit state analysis. But this needs to be checked with the building codes.